Okay, we're here today. It's September 20th, 2023, and we're going to be talking with Professor Rob Messinger at CCNY's Chemical Engineering Department. And Rob, we're happy to have you here. We're looking forward to hearing you tell us about your life, your students, and other things that you're going to share with the outside world. So why don't you start out with telling us a little bit about your life, your passage to get here.
Great. Well, thanks for having me. It's good to be here. Yeah, so I'm originally from Cincinnati, Ohio, and then I did a bachelor's in chemical engineering at The Ohio State University, where I also did some undergraduate research in microfluidic systems, and I co-opted and worked about in net 1 year at Procter & Gamble. So I really love that industry experience in my time at P&G, and then I really wanted to go very deeply into problems. I really liked chemistry, I liked physics, I liked math, I liked engineering, and chemical engineering was really the discipline for me that sort of united all these things.
Yes.
So I decided to get a PhD, and I went to University of California, Santa Barbara, UCSB, for graduate school. And there I worked with Professors Brad Schmelke and Todd Squires. And so there I worked on a few different problems. I worked on molecular level understanding and multi-scale understanding of hierarchically structured materials and processes, particularly surfactant and blockopolymer templated mesoporous materials such as mesoporous silicas, organosilicas, or zeolites with mesostructural order, so both crystalline and mesostructural order. And there I got really interested in understanding experimentally at a molecular level how these very complex materials not only were formed but how they function. And it got me interested in thinking on those length scales up from the atomic length scale really, but particularly atomic, molecular, and mesoscopic. And then with Todd Squires I worked on modeling microfluidic systems in transport, particularly electrokinetic flows and electrokinetic phenomena. And so my time at Santa Barbara was really, really enriching, and I got time to dive deeply into problems. And then when it came time to finish, I did a postdoc. So I decided, I went to grad school and I decided I wanted to move to the Bay Area and do work for a startup company and ideally direct R&D. By the time I finished grad school, I'm like, I really like the university environment. I love fundamental research, I love applied research, I love teaching, through TAing. I like the whole facet. So I said, all right, let's do a postdoc and go for academics. So I went to the CNRS in France and did a Marie Curie postdoc there for 2 years in Orléans in France. Yes. And there I decided, okay, I really liked also physical chemistry, and I wanted to, a technique that I used often in my PhD is solid state nuclear magnetic resonance spectroscopy, or solid state NMR. So very similar physics to MRI, but we do spectroscopy and we look at molecular composition, structures, and dynamics. And I thought, okay, if I could really take a couple of years and dive into it, right, and learn how to work under the hood, I can then go back and apply these to problems of chemical engineering interest, right? And I was doing that during my PhD, but I really wanted to sort of dive into that. So that's what I did for 2 years in Orléans, and I worked with Michael Deschamps and Dominique Massiot there in an NMR group and really an NMR community in France. And then during that time, I started working on battery materials, which I did not do during my PhD. I worked on materials for really the applications were more for heterogeneous catalysis or adsorption. And then I got interested in saying, all right, if I'm going to go back and be a chemical engineering professor, it'd be great to make a battery, learn how to make it, learn how to characterize it electrochemically, and sort of bring in some of the physics I was learning a little bit with with Todd Squires, but then combine it and actually learn some electrochemistry. So then I went for a year to the CNRS in Grenoble and had a position with the Grenoble Institute of Technology, and in the CNRS, a sort of combined position where I was working on block-polymer electrolytes for lithium metal batteries. And so then eventually I went to AICHE and I met Sanjoy Banerjee and Elizabeth Bittinger there, and long story short, the following year I ended up here at City College in New York. It ended up being, I was really impressed with CCNY, the faculty, the facilities, and I felt that it was a good home, people who were thinking very deeply about problems here in terms of chemical engineering fundamentals. So I felt very much at home. And yeah, so I started here in August 2015. So as an assistant professor. So yeah, so from Ohio to California to France and then to here into New York.
Those really varied backgrounds with lots of different things in them really make wonderful professors and researchers in general.
We try.
No, that's very good. Okay, so now with that very nice story about your background, what actually are you working on with your students these days?
Yeah, so my research team, we study electrochemical materials and processes, as well as multi-phase fluids, aimed at solving major challenges in energy in the environment. Thematically, I think we're sort of a combination of electrochemical engineering, physical chemistry, and materials science. And within all of the different projects, there is an underlying strategy, which is to understand materials and transport processes up from the molecular level, particularly at the, I would say, the atomic, molecular, and nanoscale levels. And so that's sort of the strategy that underpins everything. And then broadly, research can be divided into, I would say, 3 thrusts within the group. The first thrust is on novel battery chemistries. And so this is interesting because I'm interested, and many folks in my team are interested in sort of new and evolving, emerging electrochemical energy storage technologies. So within that thrust, about half my team is focused on some level on rechargeable aluminum metal batteries. So I'll talk a little bit more about that in a second. But that's it's a fascinating field. It's young, but there's not a whole lot of folks doing it. And so there's wide open space, both technologically and scientifically. We work on advanced lithium battery chemistries, particularly for extreme environments. So extreme temperatures, high temperatures, low temperatures, radiation, fast charging, with applications ranging for robotic spacecraft with NASA JPL to electric vehicles. And then also work on zinc batteries, both for extreme conditions, as well as aqueous zinc MnO2 in collaborations with professors Sanjoy Banerjee and Alex Kouzes here. So that's sort of the first thrust, and I might touch a little bit more on that. And then the second thrust is on multi-phase fluids for either thermal energy or recycling. And so there we have projects in phase change nanoemulsions for thermal energy storage. So effectively heat transfer fluids where you store energy in the latent heat of the phase change. But by incorporating them into a fluid, so for example, oil-water emulsions, and so it can be something cheap like paraffin wax or beeswax or things like this. But the idea for us is to understand from the molecular level what governs phase instabilities in these materials, which limits their technological applications for under thermal cycling, so it's sort of like a battery where you charge, discharge, or shear. And also have some projects in sort of multi-phase fluid realm looking in recycling, so one in peptide surfactants for rare earth element recycling, and that's in collaboration with Charles Maldarelli here in Ray 2 and Elizabeth Bittinger, and that's in a broader team with UPenn and Kate Stebby and her team there. and also with lithium-ion battery recycling with Ju Cheng Guo from UC Riverside. So they were working on novel chemistries for looking at solving the lithium-ion battery recycling problem, which is a tough one, but it's exciting. So that's the second one. And then the third one is in novel and advanced methods in nuclear magnetic resonance spectroscopy, or NMR, applied to energy materials. And so there we look at understanding experimentally batteries up from the molecular level, or materials including batteries, as well as the materials I mentioned before, these phase change nanoemulsions, peptide surfactants, lithium-ion battery recycling processes. And there we have a particular expertise in, I would say, multidimensional solid-state NMR spectroscopy, dipolar-mediated and multiple quantum methods, really trying to understand local structures, dynamics, compositions, amorphous phases, interphases, including electrochemical interphases. And so we really specialize in either applying state-of-the-art methods as well as doing some method development ourselves. So sort of in summary, it's sort of advanced batteries, chemistries, multi-phase fluids, and NMR. And so there NMR, we work on our own materials as well as those with collaborators.
So if a student comes and joins your group, how do they figure out what they really would like to do?
Okay, that's a good question. So if they come to me, so there's always the first answer. Part of it's available depending on what's funded and what's open. But really the deeper answer, I think, there that you're looking for is you first kind of tease out their interests, right? And so they'll generally have both a scientific and a technological interest. And so if someone's interested in batteries, why are they interested in batteries, right? Are they interested in sort of new chemistries? Are they interested, for example, in the aluminum battery problem that we're working on, right? Why are we studying aluminum batteries? Well, aluminum is the most abundant metal in the Earth's crust. It's energy dense. It's inherently safe, right? It's so safe you can, most people have some in their pocket right now, right, with their cell phone or, it's a mature mining and recycling industry, right? So why doesn't everyone use it, right? And the answer is the electrochemistry is very complex, right? Aluminum is so stable. And that stability really makes it challenging electrochemically to access that. So you need the right electrolytes, and then therefore you have to have the right cathode material, aluminum's the anode, to work with it. And so when you start talking to a student or potential student, are these the sort of scientific questions that drive them? Are they driven by the technology? Okay, making and developing an earth-abundant aluminum battery or earth-abundant metal battery chemistry? Are they governed by are they interested by, hey, I want to work on new chemistries, new charge, a lot of what we do in these new chemistries, by the way, is look at ionic and electronic charge storage mechanisms, because a lot of times they're not known. If you look at an aluminum organic battery, for example, right? And so we've been working on these problems, aluminum sulfur, right? We've made contributions to aluminum graphite, aluminum conducting polymer, and a lot of times it's not really known. If that's what drives them, we steer them that way. But maybe in the battery they're more interested by, we work, for example, with NASA JPL extensively, and I direct the NASA CCNY Center for Advanced Batteries for Space here. Are they really driven by the application? And in this case, they may be driven by batteries for robotic spacecraft. Well, what inhibits them from working, right? What limits the scope of their applications? And a lot of times it's these extreme conditions, right? So again, you kind of look at scientifically or technologically what they're interested in. Or same thing with electric vehicles, right? They may be very, very focused on, hey, what's happening right now, right here on Earth, right? And want to have something that's going to be have a higher TRL, technology readiness level. So that's sort of in the battery side. Same thing, maybe they're more interested in the recycling problem. Maybe they're more interested in the physical chemistry, right? And they say, okay, the application's cool, but really I'm interested in experimental understanding. How do we measure that? How do I characterize molecular level structures at an interface? How do I leveraged, let's say, through space or through bond interactions to really understand them. For some people, the techniques, the characterization is what drives them. So I think the key for a faculty member and for a student, right? For the student, it's saying, hey, do a deep dive. What really drives you, right? Why are you here? What interests you? For the faculty, is to sort of take what the project that's available for funding and marry that with their interest, right? Because you can always find overlap, and then everybody wins.
Okay, well put. So, what's it like for your students living in New York, working here? It's a different kind of lifestyle than Ohio State University.
Yes, and UCSB. Yep. All three very different.
Yeah.
So what's it like? Okay, so what's like? So there's the general, hey, living in New York and learning and leveraging the subway and the city. I mean, New York is a fantastic place to live. I mean, it's just so diverse in terms of culture and food and music and things like that. So I think personally, all of them enjoy living in New York, right? And no matter where you're from, whether you're from rural Ohio, right, or even from the five boroughs, I mean, New York has so much to offer. And so I think it's really personally, everyone that's come through the group is really love New York. In terms of working in my group, we have effectively two labs. We have a materials, sort of an electrochemical materials and devices lab, where we do a lot of the advanced battery chemistry development. So we work on aluminum batteries, lithium, and zinc, as I mentioned. We also work on some of the recycling chemistries there. But there's also, I direct the solid state NMR at the CUNY Advanced Science Research Center, the CUNY Advanced ASRC. And so about the other half of the lab's over there. So we have our own NMR probe and work on the spectrometer there. And so that's a really key part of the lab. And I would say more broadly, when you zoom out, a lot of my students use the advanced scientific equipment, which any student here can leverage, right, at the CUNY Advanced Science Research Center. And so there's things, from NMR spectrometers to a nice imaging from transmission electron microscopy, for example, and more to surface science. So a lot of my students also do surface science, which is XPS and time-of-flight sims, just kind of understand the chemistry and compositions at surfaces, and many more, which you can find online. And so so my students run between a few different labs that what we call the battery lab here, the solid state NMR lab, and the other sort of characterization on campus. We also, by the way, recently got a diffusion NMR probe for looking at transport processes and quantifying diffusion of molecular and ionic and atomic species, either in liquids or in solids. And so that's in the CDI, which is at the CCNY building right next to the ASRC down on South Campus. Yeah.
Wow. Very varied.
So they get a lot of exercise.
Yeah, they get a lot of exercise,
going back and forth. And really it's about giving them the tools to succeed.
Yeah, that's true. Especially if they wind up in industry, they're going to meet things, no matter what they've done here, that are going to be different, and they need to know how to deal with a new problem.
Right.
So in that respect, you're still pretty new here. Have you had some students that have already finished up?
Yeah, I have. I've actually had 4 PhD students graduate. So my first 2 PhD students, Jeff Shu and Encore Jadav, have both graduated and gone on to industry. And so, and boy, was I lucky to have those 2.
What kind of companies is that?
So Jeff is working for a startup company called Lighten in the Bay Area, and they specialize in all sorts of different carbons and graphene and graphene-like materials. And so a large part of his role is developing and pushing the field of lithium-sulfur batteries, but using his expertise he developed working on aluminum graphite batteries here. It's really a new technology, aluminum graphite, and there weren't many people working on it when Jeff and I sat down to do it. and he developed a lot of expertise in graphites and carbon. So he's working at Lighton, and he's doing very well. I'm going to have dinner with him later in November when I'm out there in San Jose. Ankur Jadhav works at Intel, and he worked on multivalent ion intercalation, particularly aluminum, in for a direct analogy to lithium ion. But he also did quite a bit of solid state NMR and electronic understanding, experimental understanding of electronic structure of materials and how the coupling ionic electronic charge storage mechanism. So when Encore, Intel wanted to hire him, not only for his experimental work and his expertise in that aspect, but he did so much troubleshooting, right? Helping set up the lab of a young assistant professor, right? That Intel was fascinated by his ability to troubleshoot experimental equipment quickly, because right now, you know, where he works, if the fab goes down, right, or if process goes down, there's a lot of money burning per minute. Brendan Hawkins was co-advised by Sanjoy Banerjee in I, and he both did aqueous zinc MnO2 systems as well as zinc ionic liquid. He's working for Urban Electric Power, which is Sanjoy Banerjee and Alex Koussis' startup, battery startup, so here in town in Pearl River. And actually, I also want to mention Mike DeAmbros, who was co-advised by Sanjoy Banerjee and I. He was a little bit more in the Banerjee Center of Gravity, and he's doing consulting here in the city in large-scale energy storage systems. And then recently, Leo Gordon from my group graduated with a PhD in chemical engineering, and he is doing a postdoc at UC Santa Barbara.
Okay.
And he is working now on lithium-ion battery systems in polymer systems, and so he's working on quantifying and understanding lithium-ion transport in advanced electrolytes, including polymer electrolytes there. He's working with Raphael Clément there. So, and he's interested in academics, and we'll see. He's you know, thinking, so it's going to be really fun to follow where Leo goes. I miss all of them. You know, I mean, just the amount of just, you know, intellectual contributions in energy and ideas they all brought, and so I miss them all. And yeah, they're going to go off, and they're already doing great things, and soon others will too.
Do they get a chance to work in other labs, either in the U.S. or overseas during that time as grad students?
Good question. There was actually plans for that, but there was something called the COVID-19 pandemic that sort of changed things. As one concrete example, Jeff Shue won a prestigious DOE fellowship to do neutron scattering at Oak Ridge National Labs. And that was a bit derailed. I mean, there was some degree he was able to do that a bit remotely. But, yes, a lot of my students do. So in fact, I've sent a large part of my team through the NASA CCNY Center for Advanced Battery Space to do 6-month doctoral internships at NASA JPL with the Electrochemical Technologies group there. And that group is fantastic. I mean, they are small, lean, and mean, and they are the group that develops and manages all of the battery systems for all the robotic spacecraft. Right? So in all of the robotic spacecraft that go, they have power systems, right? And within that power system, usually the battery is a key component. And what's been cool is so Brendan Hawkins has gone. He was the one that's now working at Urban Electric Power. Brian Chen, Harrison Asari, Lolith Robinson, Jonah Wang, all have done 6-month internships there. And right now, Michael Keating is there, co-advised with Elizabeth Bittinger. Other concrete examples, so I'm also a co-PI on our NSF PIRE award here, which involves multi-phase fluids for energy applications with Masahiro Kawaji, who's the PI in mechanical engineering, and Jeff Morris, Sanjoy Banerjee, and others here. And so Jay Park, my student, has gone to Germany, to the IPF in Dresden in Germany, to work with Dr. Ulrich Schaler doing Rio NMR and MRI velocimetry to understand how these phase-change nanoemulsions for thermal energy storage behave not only thermal cycling, which you're doing here, but under shear. And so that's, again, been really, really unique. So I've sent a lot of students on 6-month internships. And I've also sent undergrad students to NASA in different centers, JPL, Goddard, Marshall, Kennedy, working on different problems. There's one this summer who was working on moon rocks. Literally samples brought back from the Apollo mission.
Wow.
Yeah. And as an undergraduate research intern. So yeah, pretty broad, and there's more collaborations sort of in the works, so I'm hoping to send more students soon, both to California and into
Yeah,
Europe.
it seems to be a common theme. This department really likes to get the students exposed to other labs and other ideas.
It is a common theme here at CCNY Chemical Engineering. A lot of our faculty proactively seek to send our students out, whether it's in industry, national lab, or in other academic labs.
That's great.
Yeah, and we'll continue that.
Okay, so let me ask you this. So if someone is watching this video and is a prospective student and sees this and says, CCNY might be an interesting place, maybe even working with Rob might be a possibility, what suggestions would you have for them?
Good question. What suggestions? So my first suggestion is actually pertains to anyone looking at graduate school. And that's, so there's a few, so there's really 3 core factors. So one, you want to make sure that there's multiple projects that multiple faculty and projects that you're interested in working for. So you don't want to just put all your beans or all your eggs in one basket, right? So you want to make sure there's multiple people. And then 2, you want to make sure that there's the scientific and shared sort of infrastructure, so that if you go there, do they have the resources for you to be successful? And in fact, let me just address those 2 before I get to the kicker here. Those 2, I think, if you look at the diversity, specifically talking about CCNY, of our faculty research, if you look at the problems we're working on in energy and the environment, colloids and materials and interfaces, as well as in the bio area and biotechnology and biochemical processes, we have quite a diverse set of projects. And then within those thrusts, we have multiple faculty. So I think if you're interested in those areas, we're a good place. And then if you look at resources, right, we have a lot of really unique shared scientific major research instrumentations, whether it's at the CUNY Advanced Science Research Center, the Division of Science, in Marshak, in engineering here at GSOE, within the department, and then also in the PI's lab. And so, yes, make sure there's multiple faculty. Yes, make sure they have the resources. And then a third one, and I think this is general but also unique to CCNY, make sure, right? Because you can say, all right, this university and this university, and okay, we whittled it down, these 2, 3, these check these boxes. But then, make sure that if you're going to go somewhere and work there for 5 years, you're going to be happy. And so and this is tough for people in science and engineering, there has to be an almost irrational factor, right? Does it excite you? Does it energize you? Is this a place? Because if you're going to be happy, you're going to be successful. And then you have to start looking at things like the graduate student body. Do they seem happy? And one of the unique things here is our grad students have such a sense of community, right? They're involved, just socially, scientifically, professionally, and it's one of my favorite times is to go to a PhD at Defense and look at the acknowledgments. And our students will spend like 10 minutes on the acknowledgments, slide after slide after slide, and it comes from the heart, right? And so make sure when you're looking at a place, you're going to be happy. Right? You're going to be happy in the grad student body. Am I going to be happy in New York City, for example, right? And I think personally that we're a fantastic place to spend for your PhD, because there's so many opportunities and there's so much free stuff, by the way, all over New York. It's crazy, from music to food, to whatnot. And so I think if you look at those things, faculty/projects, resources, and the irrational factor, then you should really look at, I think we're a really fascinating place, but only you can answer, right, that those three questions, including the third one.
Good, thank you. That's very wise, sage advice. Okay, so Rob, thank you for your comments so far. Let me ask you before we end, do you have any further comments, suggestions, or things that we haven't quite touched on so far that you'd like to add?
Yeah, I think for anyone looking at CCNY chemical engineering, reach out. Like, send us an email, right? And we can organize, for you to come visit, talk to our students, talk to our faculty, tour the labs, don't be shy. Start asking questions now. So reach out, send us an email, give us a call. We can coordinate it, get engaged. There's really no reason not to learn more.
Okay. Well, thank you so much for your time today and for a very interesting discussion. We appreciate it.
Thanks, my pleasure.